that we had discussed earlier. And the two important things that I like to go over are SAR and the circuitry for D2A. But before we do that, let's just quickly review what we had for the formulas, which is the basic of everything that we do. The digital resolution, so if I want to summarize it down here, that we have, where is it? Draw. Okay, so if you have, let's say, n equal to 10, and your voltage range is from 0 to 13 volts, this is what I am planning to use right now, 14, 0 to 14 volts. Then what is your digital resolution? Do you remember? The digital resolution is n. It's just n equal to 10. So that's your digital resolution, 10 bits we would usually say. Your analog resolution had many names. One of them was voltage resolution. The other one was analog resolution. Another name was LSB voltage, because that's like the smallest amount of voltage that when it changes, you go from one digital number to another. So analog resolution was the 14 minus 0, your voltage range, divided by digital range, which for us here would be 2 to the 10 minus 1. As you can see, from especially for big tens like this, that minus 1 does not make much of a difference, because all the numbers, imagine if that minus 1 exists or not, it won't change much. And therefore, in fact, a lot of times when we are doing our computations, we can just ignore that. This, what I'm just saying right now, is an important concept when we go to do the SAR. Because when we do SAR by hand, we are usually doing it for small n's. And for a small n, that minus 1 makes a difference. But for big n's, that minus 1 doesn't make any difference. And most of the time, we completely ignore it when we want to do our operations. And you'll see that soon in SAR. So that's your basic general formula. And for this, and another very important thing that I would like you to always remember is this, that the digital over 2 to the n minus 1 is equal to the analog. Let's say that your Vref minus is 0 over the Vref plus. This is something that if you keep in mind, everything else you can get it from here. Yes? The analog voltage, so VA. The analog voltage, and if you have an over here, I'm assuming Vref minus is 0. None of these changes when you, that changes, everything is just gonna be shifted by the amount of Vref minus. There is a very important observation from here. And that observation is that when you go from here, you can create two formulas. One of them is VA with respect to D, and that's the easy one. So you say VA is equal to 2 to the n, Vn is D times Vref plus over 2 to the n minus 1. Do you see something here that is equal to this we just calculated? What is Vref plus over 2 to the n minus 1? The analog or LSB. So this is as simple as this, D times LSB voltage. That's easy. So if you have your LSB is 0.5 volt, your digital value is 7, all you have to do is multiply and 3.5. Done. Yes?
Yeah, you said the LSB, what would the MSB be for that?
There is no MSB for this. This is only matters for the smallest step, and it just happens that a smallest step is our LSB also, because you go from 0 to LSB. But it is your analog resolution, if you like to call it that way. So there is no MSB, equivalent MSB of this. And now, so I have the VA. The other round, the other side of this formula is not as easy. And it's actually the whole complications that we have for A to D conversion. Remember how it's complicated, you have to have something and compare, etc. All of that is because of what we are going to just see right now that I'm reviewing for you. D is the floor of 2 to the n minus 1 over Vref plus times VA. Or better than this is the one I like. It's VA over LSB. So it's very, very easy. All you have to do is to just say, okay, this is my LSB. How many LSBs is in this voltage? That's your digital value. That's it. But you can't, because it's digital, you can't go with that number that you see. So you go with the floor of it. As soon as you go with something like this, truncating is not a linear operation. Why? Because if you truncate 2.99, what do you get? What do you get? 2. What if you truncate 2.1, what do you get? 2. Is this a linear operation? No, it treats people differently. And when you deal with a nonlinear operation, suddenly resistors and things that we are used to for changing values, multiplying, adding, they don't work anymore. And that makes the design of A to D complicated. Does that make sense? Like, why is it that D to A is so easy? Well, because it's a multiplication. And Ohm's law gives us any kind of multiplication we like. Why this one is hard? Because it's nonlinear, and there is no nonlinear component out there that we can just get and plug it and use it. There was a question. So the question is, what if the Vref minus was not equal to 0? The nice thing is, if Vref minus was not equal to 0, this and this would stay exactly as is, because LSB itself has Vref minus in it. Because you have the LSB, the LSB formula is like this. LSB voltage is equal to Vref plus minus Vref minus over 2 to the n minus 1. That's why I kind of like these two last ones, which I didn't teach it this way, because at the beginning I was just trying to give you the idea, and later I realized this is a lot cleaner and easier way to remember this. You start with digital resolution, you calculate your analog resolution, and then you can go from there anywhere you like. Good? Good review? Yes?
Can you go back to the LSB?
The LSB formula, yes. So now I have these two. I have my formulas. Let's look at the first thing that is easy, the D to A design. So the D to A design, first we reviewed a little bit of op-amp. This one was the simpler one, binary weighted ladder. The binary weighted ladder